Other evidence that information processing and time are linked. Well, there's this case of a patient called patient BW. As you know, these neuropsychological patients are always known by their initials. Within time perception, there's very few cases, neuropsychological cases of people having gross deficits of time perception. There's hardly any cases out there. It seems that once you get to the point where your perception of time is grossly distorted, then you've already lost a lot of other things. It seems to be one of the last things to go. Nonetheless, there is this interesting case of patient BW. So what happened was that this patient reported himself to hospital. The catalyst for it was that he was driving his car, and it didn't matter how slowly he drove, he couldn't cope with the speed of events happening around him. He wasn't able to react quickly enough, and in the end he just had to pull over. And when they took a history from him, it turned out that this slowing down of information processing had been going on for some time. So he was finding it more and more difficult to follow conversations, more and more difficult to follow films or TV programs, and he described it as if events seemed to be rushing past him. He said it was like watching the world on fast forward. So he clearly had a very slowed down information processing rate. Now it just so happened that this chap Binkowski was a friend of Bloch, and Bloch, you may have heard me mention before in the retrospective timing literature, was interested in time perception. So amazingly, they did some timing tasks on him. So he was given a temporal production task. He was told to produce 60 seconds, and they did this 5 times a day for 5 days. And his average production was 286 seconds. Okay, so his internal clock here slowed down by a factor of nearly 5. So clearly his clock was slowed down and his information processing was slowed down. Now again, we don't know that there's a causal link between the two. It could just be that both of these things were affected, but some other faculties that he had were intact. He wasn't. He was quite lucid. He didn't have any problems with days of the week or year. He didn't have any problems with other cognitive tasks. Although he did have, if I remember, he had mild neglect. The paper's very interesting and it's readable. It's well worth having a look at. So again, it's circumstantial evidence, but it's pointing in the right direction. Now you might think, well, maybe we can get some evidence here about where this internal clock is based. The problem, unfortunately, is that by the time he presented, he had a tumour in his brain in the left superior prefrontal cortex, but it was around the size of as a tennis ball. So it's not really possible to identify any specific areas. Other links, we know that dopaminergic drugs speed up the internal clock, so things like amphetamine. There's a lot of debate about how well this transfers to humans. Essentially, the dopaminergic argument doesn't transfer very well to humans. However, people who take amphetamine report increased concentration. That's the main reason why it's taken. Hyperactivity, and that time passes slowly, which would be consistent with your internal clock running faster. Although, again, we have to be careful. When people say time passes slowly, is this a prospective timing response? Is that what they're reporting, or is this a passage of time response? We don't know. But again, the evidence is going in the right or the same direction. Other links, we know that there's a decline in information processing as we age, and there's some suggestion of a slowed down clock in aging. But again, we have the problem of state change. It has to be inferred. We can infer it to an extent from verbal estimation, but that comes with a lot of assumptions. And there's not many studies that have looked at it. There's a couple that have looked at verbal estimation in the elderly. One is published in French, and the other I think was a master's dissertation, which I managed to dig up years ago. And they did show the results going in the right direction. So elderly people tended to underestimate durations in verbal estimation, which is suggestive of a slower internal clock. So again, it's going in generally the right direction, but it's quite hard to really pinpoint these things. Other clues to what might be going on? We know that click trains can also increase other things. They can increase the judgment of line length and the judgment of number. So if I present you with a line on the screen and take it away again, and I ask you to estimate how long that line was, or if I present a load of dots on the screen and take them away and ask you how many dots are there, then clicks increase your estimation of the length and your estimation of number, but only under particularly specific circumstances. If I just do as I said, I just present the line preceded by clicks, I'll find no effect whatsoever. But if I show you a series of lines, one after the other, and I ask you to add all of those together and estimate the added together length, then the clicks do have an effect. And this is the same with number. If I just present all of the dots at once, preceded by clicks, I find no effect. But if I present some dots followed by some other dots followed by some other dots, okay, and ask you to add all of those together, then the clicks do have an effect. So this is quite intriguing. This suggests that when you make line length and number similar to time, in the fact that it has to be accumulated, then you get the effect of the clicks. So it may be that the clicks are in some way affecting accumulation rather than affecting pacemaker speed or information processing, if that's what time is based on. However, it's difficult to see how you get a slope effect from affecting accumulation processes, but there may be a way. There may be a way. We also know that clicks increase velocity judgments. So this is actually the opposite of what you'd expect. If you're getting people to estimate the speed of something, if you speed up their internal clock, then the object should appear to move slower, but they don't. People say that they move quicker. They also increase the duration judgments of moving stimuli. So it seems that velocity is estimated independent of the internal clock. Otherwise, you would find that clicks decrease velocity judgments. So again, so just another piece of the jigsaw that we're trying to fit together here. Okay, so again, we're still trying to bang our heads against what is the relationship between internal clock speed and information processing speed. There's lots of circumstantial evidence, but the causal relationship is very difficult to get at. And this isn't unique in psychology. The causal relationship is always the most difficult thing to get at. Other things we might investigate, or if you like, we can investigate from a different point of view. Instead of looking at the internal clock speed, let's think now about information processing speed and different ways we can measure that. A fundamental way in which we might measure it is by using what's called critical flicker fusion frequency threshold. It's a bit of a mouthful. But this is the lowest frequency at which a flickering light source is seen as constant. So if I present you with a flashing light, and I speed up the frequency of those flashes, at some point you won't be able to see the individual flashes, you'll just see a steady light. So the lowest frequency at which that happens, that is your critical flicker fusion frequency threshold. It's a measure of how quickly you can process the visual information. So the faster your visual processing, the higher this rate will be. And we know that different species of animals have different rates. So for the human being, it's around 60 Hertz. For the dog, it's around 80 Hertz. For a housefly, it's 250 Hertz. Now, we have to be careful about projecting consciousness on other animals. But to some extent, you could say that the housefly sees the world in slow motion. It processes the visual information so quickly that the world around it might appear to the fly to be moving in slow motion. Which might be why it's so difficult to swat the fly, because your hand coming down, the fly is sampling its visual input at such a fast rate that it's going to be able to move out in time. It's not going to be caught out by your hand moving towards it. So the housefly is a bit of an extreme. There's an even bigger extreme, which is the tiger beetle. So this is the fastest moving creature on Earth relative to its body length. So its top speed is 1.8 meters per second, which is around 4 miles an hour. And that's the equivalent of 171 body lengths per second. Okay, in relative terms, it moves at 748 miles an hour. If you compare that to something like Usain Bolt, I think he's still the fastest 100 metres runner. At his peak, he runs at 27 miles an hour, and that's around 6 body lengths per second. So this little creature really moves. But evolution has played a bit of a trick on this beetle, because it can run faster than its visual system can process information. So every so often, the beetle will run along, and then it has to stop, look around, take in its information, and then run. While it's running, it can't really see. Everything's a blur. It can't take in the information quickly. It can run quicker than it can see. And sort of going alongside this, there's an interesting paper came out in Nature in 2013, which discussed this idea. So different animals having different sampling rates of their visual system. So for example, in this diagram, this will be the movement of a squirrel. And squirrels have very fast visual processing. So if the squirrel is watching another squirrel, and it's going to sample this so fast that it's going to monitor. It's going to be able to track the movement very, very well. It's not going to track every individual movement, but it's generally going to track it quite well. Whereas an animal which has a lower sampling rate will only be able to sample the gross movement, not the fine movement. And if you lay out the different species of animals and their critical fusion frequency, then you get a line that looks like this. Now, what's intriguing about this is that this ladder, or this line, if you like, of increasing critical fusion frequency, is correlated with metabolic rate. So animals which are slow moving and have low metabolic rates seem also to have low critical fusion frequency. They sample at a lower rate, whereas high mass specific metabolic rate, animals with high metabolic rate also have processed visual information more quickly. Now, what's even more intriguing than this, now this really is a bit of a stretch, but there's a link or correlation between metabolic rate and lifespan. So animals which have low metabolic rate and low fusion frequency thresholds, so high frequency have low sampling rate of visual information, tend to live for a long time, whereas animals which have high metabolic rate and high sampling of visual information have short lifespans. So you could make the argument that regardless of lifespan, all animals process roughly the same amount of visual information during their lifetime, because the animals which live for longer sample at a lower rate, and the animals that live for a shorter period of time sample at a faster rate. So maybe relative, to each other, all animals experience the same length of lifetime, regardless of how long it actually is. That's a bit of a conjecture, but it's interesting how these things correlate with each other. There's other work on temporal processing across species, which seems to follow this pattern. And this might relate back to some of the things I've talked about in other lectures. So this idea, and earlier in this lecture, it might be that in these extreme situations, such as car crashes or bullet time, or in high-speed racket sports, that either through the fight or flight response or through training, you've increased the visual processing speed, and that's why events seem to slow down. And perhaps that could be independent of clock speed, or it could be that we don't have an internal clock and the processing of information is our pacemaker. So a question you could ask here, and this is a question that I have asked and I haven't answered yet because I've not done the experiment, is do click trains increase flicker fusion threshold? If I speed up your internal clock, does it increase the rate at which you can process visual information as measured by this fundamental critical flicker fusion? We know that CFFs are not limited by the retinal cells, okay? So there's not a hard limit on how quickly you can process visual information set by your retina. It's set at the cortical level. And there seems to be an upper limit around 120 hertz. We know this because we can increase it pharmacologically. So it is open to manipulation. So there is headroom there. If clicks exert an effect, we should be able to measure it. So that's something I'm going to be looking at very soon. Okay, so just to wrap this up, this lecture is really talking about quite experimental things, that we're trying to make this link between the lab and life, just as the title of the course suggests. And this is kind of the bleeding edge, if you like, of some of this research. So future directions, things that we're going to be looking at in my lab. We're going to investigate manipulations of CFF using repetitive stimulation, both clicks and flickers. There's also a related phenomena to critical flicker fusion, which is auditory flutter. So if I play you a tone, a beep, 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 at some point you won't be able to distinguish the individual beeps. It will just sound like a continuous tone. Okay? And we could look at that as well, so not just visual but auditory processing speeds. We could look at correlations between different thresholds and reaction times and other measures. To an extent, I've done some of this work and there doesn't seem to be a very strong correlation. If you're interested in that, then look at the work of Emily Williams, who is a past PhD student of mine. I'm going to be doing some ERP, EEG work on the effect of repetitive stimulation on both time and processing rate, on both reaction time and on CFF, and also further to investigate the parameters of repetitive stimulation. What exactly is it about the repetitive stimulation which is key to causing its effect? We know that the frequency doesn't seem to be super critical, but maybe there are other aspects of it which we can manipulate. Maybe the intensity of it is important. Okay, that's it for this lecture. I hope you found that interesting. Thanks for listening, and I'll see you on the next one.